Yeah, people? Yeah, okay. Okay, so we were kind of going through the schematic of a triple axis instrument, and I was just pointing out some of the features in it. And again, very modular instrument. A lot of these pieces, these are mounted on optical benches. A lot of these pieces can be taken, swapped in and out. And so the other feature that you'll tend to see in these instruments are filters. And there's different types of filters. The ones that you see most commonly are pyrolytic graphite filters and beryllium filters. And these can be inserted. So these are, basically pieces of material which are typically a couple of inches across that you pass the beam through. And their purpose is to clean up the beam. And so if the beam has things in it that are not what you want in it, so it's not as monochromatic as you'd like, you can pass it through one of these filters, and that could clean up the beam. And primarily what you're cleaning it up from is from what's referred to as harmonic contamination. So I'll describe what that is in a moment. But you can put these filters in basically anywhere that you have some space to do so. So you can put one in here if you wanted. So that would be before the monochromator. You could put it between the monochromator and the sample. You could put it between the sample and the second monochromator, and so forth. And so the purpose of these filters is that the monochromators that you're using are using Bragg's law, and Bragg's law is not lambda equals 2d sine theta. Okay, it's n lambda equals 2d sine theta. So every integer multiple of lambda will satisfy constructive interference for 2d sine theta. So you simultaneously get lambda, lambda by 2, lambda by 3, reflecting for the same conditions off of your monochromator crystal. That is, you get lambda, lambda by 2, lambda by 3, lambda by 4, and so forth, provided there is lambda by 2, lambda by 3, lambda by 4 in your incident beam. So as I was mentioning before, the source, the source of neutrons that you're looking at will have a certain spectrum in it. It's not really white. So if you were looking at a thermal spectrum, okay, and your lambda, the lambda that you thought you were picking out, was this lambda here. So lambda by 2 is a higher energy, lambda by 3 is a higher energy still. And so lambda, there's relatively a lot of lambda neutrons if you're looking at what's referred to as a thermal source. So if you're looking at basically the water that's surrounding the reactor, okay, there's a lot of these lambda neutrons, but there's also quite a lot of these lambda by 2 neutrons. Okay, there's maybe half as many. Okay, and there's virtually none of the lambda by 3 or lambda by 4 neutrons. So lambda by 3 and lambda by 4 in this example are not a problem. But if you pick out lambda from this distribution, you will also pick out lambda by 2. So what you thought was a monochromatic beam with lambda neutrons is actually this bimodal beam with lambda neutrons and about half as many lambda by 2 neutrons. So that's what you're looking out for. And the way you would tend to get around this is with a filter. And so as I mentioned, there's more than one type of filter, but they basically all work on the same principle, that there's some well-understood spectrum, transmission spectrum, for passing neutrons through the filter. So this is what the spectrum looks like for pyrolytic graphite. And so pyrolytic graphite, it's just a block of graphite. It's actually the same material that you make your monochromators out of, except the monochromators that you use are actually very thin. They're a few millimeters thick, typically. And the so-called mosaic spread, how good a crystal the pyrolytic graphite monochromators are, they're quite good. They have a mosaic spread of about ½ degree. The filter material, it's relatively thick because you're trying to filter out material, so it could be a couple of inches thick. And the mosaic spread is actually much worse than the monochromator materials. It could be easily 5 or 10 degrees. Anyway, so the transmission is well understood for these devices. So this is what the transmission looks like on a logarithmic scale as a function of energy. So this is what it looks like for lambda neutrons. Okay? So the transmission is quite high for neutrons below about 15 millielectron volts. That's for lambda neutrons. Lambda by 2, though, the transmission is, well, lower, and it has these very pronounced dips at about 14.7 MeV for both lambda by 2 and lambda by 3. Okay? So lambda by 2 and lambda by 3, the transmission is at the 0.1 and 1% level. So if you take a beam that's at 14.7 MeV, or at least that's where its lambda is, but it has this harmonic contamination, you pass it through one of these pyrolytic graphite filters, and you'll get rid of almost all the lambda by 2 and lambda by 3. Okay? So that's their purpose. And you can put them in place pretty much wherever there's space to put them in place. Okay. Okay, so then I want to talk about some of the ways that we think about doing these scattering experiments. Remember, the name of the game is to conserve energy and to conserve momentum, and we're going to want to go through the energy momentum dispersion surface of whatever the excitations are that we're interested in. So the phonon excitations, for example. So there's different ways we can do that, but one way that is it's actually very simple to think about is to keep one of momentum transfer or energy transfer to the crystal constant and vary the other one. Okay, so you might want to keep momentum transfer constant and vary energy transfer, or energy transfer constant and vary momentum transfer. I'm going to talk about keeping momentum transfer constant and varying energy. And the way you can do that, just by using the same sort of diagrams that we had before, is we can have what's referred to as constant KF, or constant final wave vector, where all the final wave vectors of the neutrons, okay, they all have the same magnitudes. So all these minus K1s that you've got here, these are the scattered neutron wave vectors. They're all the same magnitude, but their direction is changing. Okay? And so we're varying the initial neutron wave vector, its magnitude, but we're keeping the scattered neutron magnitude the same in such a way that all of these converge at the same incident wave vector minus scattered wave vector. So they're all at the same Q, but you have different energy transfers. So that's how you do it, keeping KF final, KF constant. This is how you do it, keeping Ki constant. Okay, but it's all just it's all just drawing these incident and scattered wave vectors and their difference. It's just drawing it out graphically, and both of these will produce the same constant momentum transfer, but with different energy transfers. So now we're going to, as I say, think about our scattering experiment by thinking about our crystal, okay, in reciprocal space. So our crystal is in momentum space. Momentum space and reciprocal space are the same thing. Okay, this has, there's a dimension here that's 2 pi over A. So if your lattice parameter is, say, 5 angstroms, 2 pi is about 6. So this is about 1.1 or 1.2 inverse angstroms across. Okay, our wave vectors are 2 pi over the wavelength. That's their magnitude. So if the wavelength of the neutron is about, let's call it 3 angstroms to make life easy. It's, if we were working with a pyrolytic graphite filter wavelength, it might be 2.37 angstroms. But let's think of it as 3 angstroms, because 2 pi, which is 6 divided by 3, gives us a magnitude of the neutron wave vector, which is about 2 inverse angstroms. So we can superpose a wave vector, an incident or scattered wave vector of 2 inverse angstroms on this plot, and we can actually draw things out to scale. Okay, and so that's what I've done here. I've drawn these out to scale. I've just superposed them. So again, we have some origin in reciprocal space, which we keep fixed. If we were to rotate the sample, we keep this atom fixed, and we rotate the atoms around it. Okay, so the reciprocal space is the crystal. The Ki's, or the K0s, and the minus K1s, that's the spectrometer. So this is keeping the momentum transfer fixed at a reciprocal lattice vector, okay, and changing the energy transfer, okay? Because for some of these incident wave vectors minus Ki's, the scattered wave vector has a larger magnitude than the initial wave vector. Okay, that means that the scattered energy is higher than the initial energy, and for some of them, it's the other way around. Okay, so what this is doing then, oh yeah, so let's, before we do that, so let's now rotate our crystal. So keep everything else the same, rotate our crystal. Rotating our crystal means rotating the reciprocal lattice only. So we rotate the reciprocal lattice, and now our Q is actually not sitting at one of these reciprocal lattice vectors. It's not sitting here. It's sitting out over here in the middle of the zone. All we've done is we've rotated the sample table. Okay, we've kept everything else the same. Okay, and now we're sitting at this particular point in the middle of reciprocal space. So if our elementary excitations look like this, so here's energy versus momentum. This would be a reciprocal lattice vector here. This would be another reciprocal lattice vector. This would be another reciprocal lattice vector. You know, if we're sitting out between two reciprocal lattice vectors, we'd be sitting somewhere here. Okay, so that's the constant Q that we might be studying. And this is what we would see in the experiment. Okay? So we've arranged so that we're keeping the momentum transfer constant, and we're varying the energy transfer. Okay? And so if you did this, and it was circa 1960 or something like this, you'd be on the cusp of a Nobel Prize. Okay? And as you scanned across here, this is data for sodium. Okay? You're going to measure background. You're going to measure whatever your background is, okay, until you get to this point here, in which point the neutron is creating a transverse phonon, and then you get to the middle here. You're again going to go down to background, and then you're going to create the longitudinal phonon, and you're going to see peaks when you do that. Okay, and so by just determining where those peaks fall, okay, and so the nature of your experiment is you're going to start off here and measure at this momentum transfer, and then you're going to measure at this momentum transfer, and then maybe here and here and here, and you're going to map out the whole dispersion surface. Okay, and I should just say, maybe I'll just go back for a second. I'll just say that that's how you would do it with constant Q, so constant momentum transfer. But you could also do this with constant energy transfer, and it's the same sort of idea. And in that case, you wouldn't be cutting across in this direction. You'd be cutting across in this sort of direction. So that's the sort of strategy that you would employ, and that's the way you would think about it. And actually, it's really the way you think about the scattering experiment that is probably more important. And actually, so these, there's very effective computational tools which you now have. So you don't really necessarily have to draw all these things out for yourself. There's computational tools which will draw them all out for you, because it's really just freshman kinematics. There's nothing really more to it than that. But it's important to understand what these computational tools are doing and what your real strategy is. Okay. So I'll now discuss a few of the more practical details. And so I was talking before about what a great thing it was that neutrons are such a weak probe of matter. And it is a great thing, because it means that we can make these very hard comparisons with theory. But it also means that our samples typically have to be very big. Okay? And that's for two reasons. For one reason is that the neutron is a weak probe of matter. And the second reason is that neutron beams tend to be big. So if you're walking around, well, here at SNS and also at HIFER, the sort of typical neutron beam size is kind of like that, right? And so if your sample, if you're not filling the effective area of the neutron beam with your sample, then some of the samples are going to go whizzing, above and below your, so some of the neutrons rather are going to go whizzing above and below your sample, and they're not going to be taking part in your experiment. In fact, what you'll do is you'll set masks to stop those neutrons from going any further, because if they're not hitting your sample, the only thing they can be doing is something bad. They can be going into your background. Okay. So we want to make samples. We want to have samples that are rather big, okay, because neutron beams are big. Neutron beams can be focused, and I'll show you that in just a moment. We can focus neutron beams by having Bragg reflection not from a flat crystal, but from a curved crystal. We can focus neutrons, but you can't focus them to a spot, right? And that our beam sizes, even for focused neutrons, are relatively big, especially compared to, say, synchrotron X-ray scattering. So anyway, what that means is that we typically want to study materials which are big, and sometimes we can grow single crystals that are quite big, and we can co-align single crystals that are quite big, but sometimes we can't actually. Crystal growth is somewhat of an art as well as a science, so we can't always get what we want. And so what people sometimes do is, although they can't grow big single crystals, they can grow many small single crystals. And so they then painstakingly align all these single crystals. Just imagine what kind of a PhD thesis this would be, you know, and put them together, and in such a way that they can fill up all that space and use the neutrons effectively. Okay, so neutrons, because they're a weak probe, they're a volume probe. If you double the volume of your sample, for most samples, you'll be doubling your signal. Okay, for a neutron absorbing crystal, that's not the case. But for many samples, it's a straight win. If you double your sample, you just get twice the intensity. Okay. So the monochromators, the choices for the monochromators, you know, so here you see, well, these are kind of the, if you like, the standard monochromators. There's pyrolytic graphite, which is this thin pyrolytic graphite, has very high reflectivity. So this probably has the highest reflectivity. Its d-spacing is about 3.3 angstroms. Got beryllium, which has a much shorter d-spacing. Okay, so it gives you relatively high incident wave vectors. And then silicon, you probably know, has the diamond structure. So it doesn't have one atom per unit cell, it has 2 atoms per unit cell. And it turns out that means that for reflections, for a Bragg reflection like 111, there is no lambda by 2. So you don't need to use a filter to get rid of harmonic contamination, at least lambda by 2 contamination for silicon. These are kind of the 3 standard ones. And what you're looking for in a monochromator is you're looking for it to have high reflectivity. You want it to reflect a monochromatic beam of neutrons, you know, with a lot of neutrons in it. So you want its reflecting properties to be very high. You'd like it to be focused. You'd like to be able to manipulate the monochromator so that you could focus the beam, so that in principle you could use smaller samples just as effectively. And this shows you how that works. Actually, with graphite, with pyrolytic graphite, you can actually bend pyrolytic graphite. It's sufficiently thin that you can stress it and bend it into something that looks like a mirror, a focused mirror, and that would tend to give you a smaller spot size. With something like copper, so this is a copper monochromator. You can't bend copper. So copper, to make it into a monochromator, it needs to be relatively thick. But what you can do, and what people do, is that they cut up little single crystals which can be individually mounted and aligned in such a way that you make up this mosaic of a monochromator crystal, which then can be focused actually in 2 different, you know, both can be vertically focused and horizontally focused. So you can take your beam and effectively make it considerably smaller, considerably tighter, without losing intensity. Okay, so that's what a focused monochromator looks like. Okay. And actually people have been very clever with making monochromators which can do this, but still there's a limit to how focused the beam will be. And so a couple of centimeters in a linear dimension is about the smallest beam that you can end up working with. The other component of the detector, and you might even have a separate lecture on detectors actually, and so the detector is actually quite important. We're looking at inelastic scattering. It's typically rather weak scattering, so we want to capture every neutron that we can. We want very efficient detectors, and so the most efficient detectors are helium-3 detectors. So the reaction that's going on, so this is what a helium-3 detector looks like. So it's filled with helium-3 gas, typically at high pressure. I think the detectors on the chopper spectrometers at the SNS are 13 atmospheres, I'm going to say. Is that right, Jaime? A ballpark, okay. Okay. And so what it is, it's a tube filled with high pressure helium gas, helium-3 gas, with a wire running down the center. And the reaction is neutron plus helium-3 goes to tritium plus proton plus a gamma ray. So the tritium, so everything here will produce ionization in the gas, and that ionization, that whatever charge you get from the ionization can be collected on the wire, which is under a high voltage, and so that's a very efficient way of detecting the neutrons. And so this is what the efficiency of the detector looks like as a function of neutron energies. Okay, so of course the neutrons are, or the detectors are much more efficient detecting low energy, long wavelength neutrons than they are at high energy, short wavelength neutrons, because the high energy neutrons are going faster, so it has, if you like, less time to detect them. So you can see that the efficiency of the detector at high energies increases a lot. There's a big premium on having the helium gas at high atmospheres. And that's why the detectors at the SNS, which are often looking at neutrons that are hundreds of MeV, so hundreds of MeV are way up here, those have to be at high pressures. They have to be above 10 atmospheres of pressure. Otherwise, the efficiency is very low, and we're looking for weak signal, so we need our efficiency to be high. So these are the detectors that we use to measure our actual signal. I'll just be a second, sure. And these are the detectors that we use to measure the incident flux. We're also in normalizing per incident flux. So we want something that will tell us the incident flux, but we don't want it to take very many neutrons out of the beam in order to do so. So we actually want a low efficiency detector to be one of the first things that the neutron beam goes through, and that tells us what the neutron flux is, and actually, so that's what these look like, and these are fission counters typically. Yes? Oh, it doesn't. Yeah. So good question. So how does the helium tube detect the energy of the neutron? It's because it's a secondary reaction that it's looking at. So so basically, this detector is measuring the ionization from these products in the reaction. So it's not measuring the neutron directly. Okay. And so this process is almost independent. Well, it's not independent of the neutron's energy. You can see that it has this dependence of the neutron's energy, but it doesn't tell you what the neutron's energy is. So you're measuring the neutron's energy by the spectrometer. So in the case of the triple axis spectrometer, we're measuring the neutron energy directly by measuring the de Broglie wavelength. So we're measuring the neutrons that come off over here, and then we're using Bragg's law here to tell us what the wavelength is of the scattered neutron. So we're only using the detector to tell us that a neutron has been detected. It does not tell us what the neutron energy is. That's a very good question, actually. So for X-rays, for example, there are energy dispersive detectors. There are detectors that will tell you the energy of the neutron, of the X-ray, to within some tolerance. That doesn't exist for neutrons. Yes? Exactly. That's exactly right. Yeah, yeah. So you're just scanning through, you're scanning through essentially theta in lambda equals 2d sine theta, right? It's the d spacing is the same. It's just the d spacing of the monochromator, and so as you change theta, and you keep as you change the theta of the scattering here, and you keep the angle of incidence equal to the angle of reflection there, you'll be scanning the final energy. Exactly. Yeah. Other questions? Okay. Yeah, so I'll also just very quickly point out, because I'm not going to do this in any detail, but you're not really, of course, measuring at one particular wave vector, or sorry, one particular momentum and one particular energy. Okay, that would be a perfect instrument, and of course we don't have a perfect instrument, and we don't want a perfect instrument, because as I was saying before, if you perfectly resolved your momentum transfer and your energy transfer, you would do that at the expense of intensity. Okay, and at the end of the day, intensity is our stock in trade, right? That's what we actually plot. We plot intensity versus something, and if you throw that all away to get high resolution, you won't have anything to look at. Okay, so what we actually measure is not S of Q and omega at our target momentum transfer and energy transfer. We actually measure the convolution of this with our instrument, okay? So we actually integrate up a range of wave vectors or momentum, a range of momenta and a range of energies around our target energy in such a way that we measure the intensity, in the vicinity of our target momentum and our target energy. Okay, and so this factor here, this R function, is referred to as a resolution ellipsoid, and so this takes into account all the practical details of our instrument. What are the beam divergences? The beam doesn't go. We've got these solar slits in place, but the beam doesn't go in a precise direction. It has some angular spread. What are those angular spreads? Okay, the bigger the angular spread, the more you're going to integrate up in this function here. The collimations, the crystal mosaics, every practical consideration for every piece of the spectrometer is included in that resolution ellipsoid. Okay, and the resolution ellipsoid, what it means is that what you measure is not what you would get by taking a point and bringing it through this dispersion surface. So you don't measure a delta function when you come to this point. Okay, you don't measure nothing, 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 then something, then nothing, nothing, nothing. What you measure is the convolution of, you're going to integrate over everything that's in this ellipse, okay, as it crosses this dispersion surface. So you can see that you're going to start to cross the dispersion surface about here, okay, and you're not going to finish having crossed it until you get to here. So you're not going to measure a single point that's high. You're going to measure this peak, and the width of this peak tells you about your resolution dimensions. Okay, and you can see that if it's actually an ellipse, as it is here, as opposed to, say, a circle, and it is an ellipse, I'll tell you, then the relative orientation of the ellipse compared to the dispersion surface makes a difference. Okay? And it can be actually quite complicated. Okay, so we talked about triple axis spectroscopy, quite an important technique. But all of triple axis spectroscopy is predicated on measuring the neutron's de Broglie wavelength in order to determine its energy. Okay? But that's not the only way to do it. Okay? And the reason that's not the only way to do it is because the neutron has mass. So higher energy neutrons are moving faster, lower energy neutrons are moving slower. Okay? And so this is the relationship between the de Broglie wavelength of the neutron and its velocity. So it's roughly in kilometers per second, which sounds pretty fast, but actually it isn't. Okay, it's 4 divided by the wavelength in angstroms. Okay, so 4 angstrom neutrons are moving at about 1 kilometer a second. Okay, so pretty fast. But if you go to the instruments that we have here at SNS and any instrument that uses how fast the neutron is going in order to determine its energy, those are called time of flight spectrometers. Go to any time of flight spectrometer, and the detectors will be something like 4 meters away from the sample. Okay, so once the sample has scattered off once the neutron has scattered off the sample, it's got 4 meters to go before it hits the detectors on average. Right? Actually, some of them are 3 meters, some of them are 5 meters. So ARCS is 3 meters, Sequoia is 5 meters. I think CNCS is 4 meters. I can't remember. Anyway, so they're about 4 meters away. So and at DCS, I'm going to show you DCS as an example, just because I have good pictures of it. It's 4 meters from sample to detector, so it takes 4 milliseconds for elastically scattered neutrons with a de Broglie wavelength of 4 angstroms to travel that distance. Okay, so that sounds like you have to be pretty fast. But actually, our electronics is much faster than this, right? So this is not a problem, okay? And but the main point is that we can measure a neutron's energy and wavelength by measuring its speed, okay? And this is something that you can only do with neutrons. You can't do with X-rays, say. And so this leads to time of flight techniques. And so the time of flight techniques, so these are what are used at SNS, but they can also be used at a reactor, and some of them are. But the basic idea is that you have a white beam of neutrons, which comes in from the source, and then you you pass it through some device, and we're going to talk about a couple of these, that will select out a monochromatic beam of neutrons that's going to go towards the sample. Okay, the neutrons are going to scatter off the sample, and we're going to wallpaper as much of 4 pi steradians around the sample position with position-sensitive detectors, which will also time the arrival of the detectors. Okay, so this is the no neutron left behind approach to scattering. So what we want to do is we want to tag every single neutron that scatters off the sample with its angle of deflection and its time of arrival. Okay, and its time of arrival is going to tell us whether it's sped up or slowed down after it's scattered off the sample. And its angle of deflection is going to tell us something about how much momentum it transferred to the sample. Okay, so if I just lay out the various components here, and just with there's basically 3 components to this instrument. Okay, there's something that defines the incident neutron energy, which could be a velocity selector, could be something called a Fermi chopper, could be something called a disk chopper. They all kind of do the same thing. They basically all work like phased traffic lights. Okay, so if you come from a pretty big city, there's almost certainly some boulevard in your pretty big city which has phased traffic lights. So if you drive at 30 miles an hour, you get from one side of the city to the other without hitting a single red light. But if you drive at 20 miles an hour or 40 miles an hour, you'll hit the first red light, and you'll hit them. You know, and that's because the city, with its good intentions, has phased the traffic lights across this boulevard in such a way that, you know, one of them turns green, and then the next one turns green, and the next one turns green. And if you're going at 30 kilometers, or 30, sorry, from Canada, if you go at 30 miles an hour, you know, you'll hit nothing but green lights. And so these work in exactly the same way. Okay, so you've got something that defines the incident energy. So and it's downstream from the source. So here's the source. We produce all these neutrons. They're sort of white. You've got the very hot neutrons and the very cold neutrons. Okay, and the hot neutrons get to the Fermi chopper. That's this instrument here first, and the cold neutrons get there later. And we've set up this device so that it lets in neutrons for a specific window of time. Okay, so it's only open for a certain amount of time, and so it's going to only let in these neutrons here, these ones that are kind of orangey blue, I guess. And so you're going to get some incident wave vector or incident monochromatic beam of neutrons that goes towards the sample. Okay, once it scatters off the sample, it's not going to be monochromatic anymore, because there's going to be these inelastic processes, phonons, magnons, God knows what. Okay, and again, the ones that speed up are going to get to the detector first. The ones that slow down are going to get to the detector later. And this is the intensity that you're going to measure on your detector as a function of time. And so time here translates to energy. Okay, so we're going to measure, by measuring the time of arrival of the samples on a given detector, they're all the same distance away. So by measuring the time of arrival on a given detector, we're going to figure out the energy that we have, and they all have the same energy to begin with, so we're going to know the energy transfer. Okay. So that's how all these instruments tend to work. This just shows you, so this is the layout of the disk chopper spectrometer. So it's a little bit different at NIST. And actually, you've got all these disks, right? And there's 7 of them in total, and they're basically all like traffic lights. Okay, they've got green lights and red lights, and I'll show you them in a moment. They're spinning actually, and in order to get through, in order to run the gamut of all these choppers, okay, the neutron has to have a very well-defined average speed and distribution of speeds. And you can set that by setting the characteristics of all these choppers. Okay, so the neutrons that get through here are the ones that we want to get through, and they hit the sample all together. You get a pulse of neutrons that hits the sample. You've got these detectors. They're all at the same distance away from the sample. So it takes the same amount of time for the neutron, or sorry, it's the same distance to go from the sample to any of these detectors. And so by measuring the time of arrival at all these detectors, we can measure the speed of the neutron. Okay, so this is what these choppers basically look like schematically. They're mostly opaque. They're disks that are, so this is the neutron guide, okay? And here the disk is spinning around. You can have more than one of them spin around, so this is like the phased traffic lights that I was talking about before. You've got a neutron's can only get through when the opening is in place, and then it's got to get from here to here in time for the next opening to get in place. Okay, that's how it works. And of course, you know, these choppers, the way they're really organized is that there's two of them that run in anti-rotation with respect to each other, so that you get a better defined pulse. And and this is what it actually looks like. This is the window here, but there can be other markers. These are actually fiduciary markers on the disk, and it just spins around like this. So this is the real size of these types of devices. So that's a disk chopper. You also see Fermi choppers. Fermi choppers are much more compact. They're like little cylinders. They're spinning around. This doesn't show up very well here. But basically what they look like is they're a cylinder that's spinning around, which has these curved, it's like a curved solar slit. Okay? It's what we talked about before. So you've got these regions that are made up of neutron absorbing material, which separate these transparent channels. So again, and then this whole thing is rotating. So the neutron beam is coming through, say, in this direction. Okay? And actually, I think it has to be coming through in this direction. But at any rate, if the neutron beam enters one of these channels, if it goes too fast, it hits one wall and gets absorbed. And if it goes too slow, it gets hit by the other wall and gets absorbed. Okay. So either way, you know, there's a tolerance in terms of how fast it's going before that will define whether or not the neutron gets through. Okay. And then there's also something called a T0 chopper, which is actually usually the first thing that the neutrons see when they come off the source. And the purpose of the T0 chopper is to get rid of what's referred to as a flash at the very beginning of the spallation process. So the spallation process is actually a somewhat messy nuclear physics process, and kind of a bit like sausages that you'd probably prefer that you didn't know what was actually going on to make them. And anyway, the idea is that in the spallation process, you've got the proton beam hitting the mercury target here, and it produces this spill of neutrons. But it also produces all sorts of other nuclear processes, and a lot of them produce very energetic gamma rays and such. So that comes out right away. And that is actually so fast that it's not going to interfere with our neutrons, which are moving relatively slowly, but it's going to occur at first. And if our detectors and our instruments actually see that flash, it will disable them for long enough to mess up the experiment. So we want to get rid of the flash. So we've got this, it's kind of like, it's just really a big weight that's going to rotate and put itself into the position to intercept the flash for that first instant in time and then get out of the way after that. Okay, so that's called a T0 chopper. So if you hear people talking about the T0 chopper, it doesn't define, the Fermi chopper defines the energy resolution of the measurement and the energy resolution of your incident beam. Okay, the T0 chopper doesn't define it has nothing to do with the resolution of your instrument. It's to try to keep the instrument clear from that initial flash from the spallation process. Okay. So we've already talked about these helium-3 detectors. You can see the timing resolution is about 10 nanoseconds. Okay, so the timing resolution is good enough to measure the energy of the neutron to typically within about something like 2 to 3% of the energy of the initial energy of the neutron. Okay, So if you're doing an inelastic neutron scattering measurement with, say, 60 MeV neutrons, it's a very common configuration to use, then your energy resolution could easily be 1 or 2% of that. Okay, so it could easily be around 1 millielectron volt, right, which is very good, actually. But your energy resolution is going to be largely determined by the timing, how well you can measure the timing. And so these detectors are about a meter high, so they're about this high. You can see these are actually detectors from ISIS, but you can see that we literally do try to wallpaper as much of 4 pi steradians around the sample position as we can with these detectors, and they're position sensitive, right? So we know when the neutron hit the detector to within 10 nanoseconds, and we know where along the detector the neutron hit to within about a centimeter. Okay, so its position, it has position sensitivity and time sensitivity, and every neutron that is scattered from the sample, what we want to do is we want to measure the neutrons in event mode. So that data point goes off, and we know where that neutron, we know the coordinates of that neutron in both space and time, so that after you've collected all this data, you can rebin it and analyze it in different ways and change your resolution, if you like, the resolution with which you're looking at the data after the fact, because you stored the information about where the neutron hit and when it hit. Okay, very powerful, very powerful. Okay, I think I'm pretty much at the end of where I want to be. Yeah, you're going to see these things coming up, and I'll just finish off with this last point on data visualization. And so the good news is that we can now measure these enormously comprehensive data sets in a relatively short amount of time. So we're talking about momentum transfer and energy transfer. Momentum is a vector. Okay, momentum in a single crystal is a vector. It's 3-dimensional. And then so your data set is going to be 4-dimensional if you're looking at a single crystal. Okay, it's 4-dimensional, and you've measured it very comprehensively with these new instruments. And so the good news is that you've measured everything, and the bad news is also that you've measured everything. And you're going to end up with a data set. So my students, one of whom is here, but my students go to these experiments and they come away with an external hard drive, which we bought at Walmart for about $120, right, 2 terabytes, and we'll fill up at least one, right? We might fill up several. And then they'll go away and they'll try to make sense out of this data, because it's a huge data set, and just visualizing the data is actually not so easy, because if you've got a 4-dimensional data set, the sorts of, even if you look at plots like this, this is 2 dimensions, okay? So to get to this point, you have to have integrated out 2 other dimensions, okay? So it's not necessarily that easy to look at, and that's just kind of looking at. This is actually a movie, but I don't think it's actually going to move. It shows this is 2 different. Well, it's data sets from the same experiment, but in one case we have a system with long-range ordered spin waves. In the other case, it's disordered. But I just like, this is a 3-dimensional representation of the data set, and the data set, as I say, is 4-dimensional. So even this is an integration of one of the dimensions. Okay, so this is energy on this scale and 2 different directions in reciprocal space on this scale. Okay, but we've integrated over the 4th dimension in order to get this data set, right? So just visualizing the data set becomes a big deal. Okay, and then there's modeling it and such. So on that, I think I'm just going to end on that point and say that these are significant challenges, but these are the challenges that we want to have, right? We got to this point because neutron scattering has evolved to the point where we can now measure these enormous data sets that are really exceedingly rich. And so we have opportunities that the previous generation simply didn't have. And so there are challenges that go along with it, and this is one of the challenges. but this is the position that you definitely want to be in. It's a very exciting position to be in. So thanks. Sure. Yeah, sounds good. Yeah, the other. I'll just mention that you're certainly welcome to come up any time to ask me questions. I'll be having lunch with you as well, so you can ask questions there if they come up.